With that, let me introduce the speaker. I'm very pleased to introduce Mike Heroux. He's a senior research scientist at ParaTools.com, has a long history, including years at Cray Research and Cray Supercomputing. Very happy to have Mike give this presentation today on scientific software from community foundations to agentic futures. So Mike, please come on screen. Thank you for joining us.
Thank you very much, Jay. Can you hear me?
Yes, everything's good.
All right, and you see my slides?
Yep, and they're in presentation mode.
Great, very good. Thank you very much. Well, thank you very much for this invitation. It's a privilege to be here, and I look forward to sharing a few ideas with you. Some of this is quite speculative, and so part of my interest in coming and presenting here is to gain connections and ideas from other people and future collaborations. So let's get started. Agentic computing is transforming how we do our work. It's incredible to see all the progress, things that are going on. I see it poised to do the same for scientific computing, and it's already starting. But I also think that some fundamentals are still present, and I'm going to focus on 4 of them: discoverability, usability, portability, and then community. And I'm going to do that through past projects that I've been a part of, a current project that I'm part of, and then try to speculate about what the future could be like. But my first assumption is that we care at all about equation-based simulation. And sometimes I wonder, because AI has captured the mind share and the budgets of the community, but I think simulation still matters, and I think it will matter even more as we go forward. In particular, world models are becoming increasingly important in even mainstream AI, and I think that simulations can contribute a lot to the development of high quality world models. Also, they're just plain the best approach for problems that have deterministic behavior. I think that we see that over and over again. So I think actually one thing that will happen as we go forward is we will have more simulation codes. We can develop them to be better, faster, and cheaper. And so we can foresee a future where even if the cost of maintaining a simulation code is less, because we have more of them, I think we'll have even more work in this space. So let's take a look at these 4 perennial themes. Discoverability is, how can I find the software I need to solve my problem? Usability is, how do I make it work for me, purpose fit? And how do I trust it? Is the team committed to quality who's producing it? Is it portable? Can I use it across all of the platforms, both now and in the future, for the problems I need to solve? And then in this scientific software world, how do developers and users and maintainers and sponsors collaborate? And so I'm going to talk about these 4 things in the past and present and looking forward. So the first project is called Trilinos. It's a project I started in the early 2000s. It's a large collection of scalable scientific software libraries and tools. It contains foundational products for the U.S. Department of Energy and the applications it supports. It's open source. It's primarily C++, and it is performance portable using the Kokkos suite of capabilities. And I have a few slides from the Trilinos user developer group TUG meetings that we've held in the past that illustrate how these principles that I mentioned were active in the early 2000s and even up until today to some extent. So first of all, Trilinos is a large collection of libraries and tools. Each of them has their own name. But this 2-level structure, Trilinos at the high level, is what many people recognize as the product, in particular our stakeholders. And so the fact that we have all these dozens of other capabilities, products in Trilinos is important, but they really think of Trilinos. But at the package level, each of these individual products has a small group of developers, and they care a lot about their community identity. And so this 2-level structure permits both discoverability and also supports teams that want to have their own identity in their research community. And it allows us to have uniformity in the essentials and flexibility elsewhere, at least in theory. There are always edges where things don't work out quite that way. Usability, access. So this is way before there were things like Git or GitHub or other ways to communicate. And so one of the very first things a package got when it joined Trilinos was this collection of tools. You know, it had its own directory, a CVS, had its own Bugzilla set up, own Bonsai, mailman lists. And so we were able to launch and quick start new projects as they came into Trilinos. And then quality, Trilinos provided a lot of backbone and support infrastructure for teams that had to satisfy the Advanced Scientific Computing Initiative, which was starting up in the mid-90s and well into the 2000s. Teams didn't have the resources or necessarily the skill to address quality on their own. And so Trilinos provided this capability and platform for addressing software quality requirements. Also within Trilinos was where the Kokkos package started. In fact, the Kokkos name was coined in 2003, long before the Kokkos that is commonly used now in the scientific community what was known. And so Kokkos started off as because we needed something that was portable. To address now multi-core and eventually GPU nodes, and Kokkos started off really as a set of requirements more than a solution to it. But over time, it gained traction and eventually was exported out of Trilinos to support the many users who needed that portability but didn't need the scientific libraries that were part of Trilinos. And then the community. So we had annual Trilinos user group meetings. We have annual meetings in Europe, and so this is opportunities for people to get together. It's very small relative to what's possible today, but it was a start in the right direction. So for Trilinos, so discoverability, new packages are instantly available. Trilinos is recognized by stakeholders, package names by their research community. For example, Zoltan was well known in the discrete math community. Usability, same infrastructure, emphasis on software quality. Portability, Kokkos, and its evolution into what it is today. And then community, the Trilinos user group. And then we had a kind of few-to-few development and support model because we had some key stakeholders that we needed to make sure we address their needs and then make it available also to the open community. So that's a little bit about Trilinos. Let's move forward to ECP. ECP was a 7-year, about $1.8 billion project to produce libraries, tools, and apps for exascale. And I argue it moved the needle for portable, scalable, GPU-based science. I was personally the director of software technology. Had about 250 scientists from DOE and labs, university, industry that work in the organization. We had a total budget of about $500 million, and we produced a 3-tiered software stack for integrating, testing, and distributing scientific libraries and tools. And this graph here depicts that structure. So at the lowest level, we had the software technology products. These were libraries and tools that have been around for decades. That part didn't change. But then we integrated those into what we called SDKs, or we now call product families, which are collections of things like math libraries or development tools or data and viz libraries and tools. And then incorporating all of that is what we call E4S. And E4S was the way we got products out to the facilities, the way we supported users, the way we integrated all of the work that we were doing into a cohesive and comprehensive collection of software. And this is essentially what E4S provided. At that time, E4S stood for the Extreme Scale Scientific Software Stack. We've reinterpreted that acronym, and I'll talk about that in a little bit. But E4S provided this collecting point based on Spack. We relied heavily on Spack. We bet on on Spack before it was clear that Spack was the thing to bet on, and we helped in the process of making Spack that thing. that a lot of people now depend upon. So that's a little bit about ECP. So discoverability, with the emergence of Spack, E4S as a stack, we had community policies that ensured software quality. We did lots of porting and regression testing on a system we call Frank, short for Frankenstein. Has lots and lots of different devices on it. That's still the backbone of a lot of our testing. Portability across GPUs. Kokkos and Raja, a similar product, and other means were how we got portability across all these platforms. For community, we had the ECP annual meeting, which if you ever had a chance to participate in, was a truly unique and interesting event. We had hundreds of people who cared about scientific software. Primarily, it was the Department of Energy and friends. So that could be other agencies, industry, some international partners as well. But it's a really vibrant environment for people who cared about scientific software. Had a very strong ECP identity to the project as a whole. ECP also was where our HPC best practices efforts, our Better Scientific Software Fellowships, and then a whole bunch of social science themes emerged. We were large enough, and we had a big enough and complicated and complex enough organization that it made sense to engage social scientists directly into our activities. All right, that was a little bit about ECP. Now I'm going to talk about a project called PESO. It's a bit of a tortured acronym, but we like the acronym itself. So we made the words fit it well. So PESO is a new, an ongoing project. Lois Kerfman McInnes is the PI from Argonne, myself, a co-PI with her, and together we lead the PESO activities. So ECP ended and things changed, and ECP was about delivering software capabilities, a stack. But after ECP, we needed to focus on sustainability, or stewardship is another word that we often use, of the software ecosystem. So we had created this thing under ECP, and now we needed to keep it and maintain it and sustain it and expand it. And that's what the post-ECP activities have been about. So PESO is a big part of that. What we are the ecosystem level coordinator and stewardship of the DOE software capabilities. Now, we do not have an overarching leadership role, but we are among peers in this activity. We provide the shared infrastructure, integration, and policy alignment. We produce two primary products, E4S, which now stands for the Ecosystem for Science, and Spack for the Office of Science. So Spack is sponsored by Lawrence Livermore National Lab primarily, but with lots of other people. It's sponsored by the National Nuclear Security Administration, NNSA, but also has an open science piece. And the PESO project sponsors that kind of activity. PESO does not directly support product teams. They have their own direct funding. We're not a hierarchical lead group. And in fact, many of PESO's efforts are branded as what's called CAS. I'll talk about CAS in a moment. And HPSF. I'll also talk about that in a moment. So PESO scope today is we work on E4S and Spack. We do lots of things to support the Consortium for the Advancement of Scientific Software, CAS, and the High Performance Software Foundation. We provide stewardship to the Department of Energy's ecosystem through our collaborations with these other organizations. As I mentioned, E4S was the extreme scale scientific software stack during ECP, and it was needed to get products integrated that were being heavily invested in the development. After ECP, we've evolved to this ecosystem for science. We provide a lot of background capabilities for the product teams who develop the math libraries, the data and viz libraries, performance tools, programming systems, other kinds of capabilities. And with the goal right now is that E4S, it succeeds when it's invisible infrastructure, that's always there, always reliable, always growing. I mentioned CAS. The Consortium for the Advancement of Scientific Software is a DOE-sponsored capability that allows teams that are doing scientific software work to collaborate with each other. So we have a lot of activities that are CAS oriented. CAS is not directly funded by anyone. Teams can opt in and participate in CAS and bring their conversations to CAS so that other people can benefit and they can learn from each other. One of the key tangible events we do in CAS is what we call the CAS BOF Days. Those occur in February each year, and these are ways for the development community, the members of CAS, to engage with the user community. Everything is online, and you can see the list of topics of the BOFs from this past year. We will do it again in February of 2027. So if you're interested in this, it's a chance to rub shoulders virtually with the developers of any of the scientific software libraries and tools that are developed under DOE funding. We also supply as part of PESO outreach to the community, so-called BSSW, or Better Scientific Software. We have a website that we produce that has lots of content related to scientific software. We also sponsor a group of fellows and select them with funding from the National Science Foundation and the Department of Energy, both NNSA and Office of Science. And so each year we have the opportunity to take applications and honor, recognize, and provide modest funding to a cohort of people who can contribute to the scientific software community through their activities. So the last thing I want to mention in the PESO space is HPSF, the High Performance Software Foundation. This is one of the more exciting developments, in my opinion, for scientific software. HPSF has grown as time has gone on, starting in May of 2024. It provides an opportunity for anybody who cares about high-performance software, especially for science and engineering, to collaborate, get together, meet, share, make progress through working groups in a lot of different areas. And PESO plays a large role in HPSF by providing some of the funding for it and many of the members who are part of this. I mentioned ECP in the annual meetings. I consider HPSF to be the unconstrained follow-on to what ECP started, and that we can have collaborations that are not just the Department of Energy and friends, but anybody on the planet who cares about high-performance software. And so it's unconstrained in the ways that ECP was somewhat constrained because it was a programmatic activity. HPSF doesn't have that. And so I foresee HPSF as the means for the scientific high-performance software community to collaborate. All right, so a little bit about PESOs in summary. Discoverability. Spack is a de facto standard now for providing thousands of installable products. HPSF provides product visibility. E4S provides this recognizable curated ecosystem. I'll talk a little bit more about what E4S provides and how you can use it. Usability, a commitment to quality through community policies. We have this Guidebot I'll talk a little bit about. We have this lightweight, portable, containerized set of capabilities. And then in portability, we continue to support NVIDIA, AMD, Intel, and maybe someday TPUs. That would be a good thing. Kokkos and Raja. So as we port to these new platforms, Kokkos in particular provides an essential role for performance portability. And then I mentioned community, the CAS, BSSW, and HPSF connections. All right, so next I want to talk about equation-based modeling and simulation in an AI world. AI for science. So some of the things we're focusing on in PESO is what I call a Guidebot. And this is a new website tool that we've created. And I'll get to that in a minute. We are also producing containers for portable turnkey use of E4S apps, libraries, and tools. And we look at AI as an ecosystem enhancement, not a distinct activity. So you'll find in E4S many AI-specific libraries and tools. We think that scientists are not going to use AI distinct from modeling and simulation or even from quantum. Instead, they're going to want access to all of these approaches to computing as they try to solve scientific problems. So we focus on this holistic activity as part of what we do in PESO and as part of E4S. I'll mention briefly the E4S website. It's e4s.io if you want to go to it. We've created a Guidebot. And what we did is we created a collection of Gemini Deep research reports for each of the product family areas. And then we injected them into a GPT, starting with OpenAI's GPT technology. And then we used that Guidebot to create the website. And so now we have this Guidebot that knows all about our products. And so using English prompts and then generating Markdown from those English prompts, we were able to stand up a brand new website for E4S. In turn, we can use this Guidebot on the site itself. It's available to users. And so this shows you the reports we created in 6 different product family areas: AI, ML, build tools, data and viz, math libraries, parallel programming tools, and perf tools. And then we added those to the Guidebot and then have this document-driven RAG approach to things. You can go to it from the e4s.io website if you have an OpenAI account and use it. It understands the scientific software and HPC context. It knows Spack. It has domain fidelity beyond generic LLMs because of its injected RAG capabilities, and it can synthesize across layers in the portfolio of distinct products. So if you want to know the best library for doing something, you can get unbiased answers from this Guidebot. That might be hard to get if you're just talking to the developers of one library or tool versus another. One of the key features of the site is that you can define, it gives you a list of attributes and their descriptions, and the extent to which you know the answers to these questions. Can you describe your problem type? Are you using other libraries right now? What kind of data structure support do you need? What kind of precision? So the extent to which you can answer these questions about your problem, you can get a very good answer from the Guidebot. So here, for example, there's a guide, a prompt guide for every single one of the product families. I'm going to look at the math libraries one for a moment. In the math libraries one, you can see this introduction. You can see an example prompt. So here's an example prompt. So again, it's trying to, the Guidebot is trying to extract through these attributes a good description from you. And you're looking for a skill. You know, I'm developing a simulation that requires solving large sparse linear systems and so on NVIDIA, you know, written in C++ and so on. And so you can give a very good description by answering the attribute, you know, providing attribute definitions for the Guidebot, and then it can give you a very good answer back as far as what library or tools to use. Okay, so that's a bit about the Guidebot. Next, I want to talk about containers. So E4S is available in many containers on a variety of Google Cloud, Amazon Cloud, and you're able to access E4S via containers. You can also download them from Docker Hub and run them locally. And so what I've done in this particular example is I've downloaded the base container for E4S. It has pointers to a Spack build cache for the full E4S. So in other words, there's a binary pre-built version of every single library and tool in E4S that this particular container is pointing to. So if you want to get access to a library or an application in E4S, you don't have to build it. Some of these libraries and tools take hours to build, but instead you can grab it from a cache. So in my particular example, I downloaded the base E4S container onto my laptop, the very same one I'm using right now. That Docker pull took 42 seconds from my home internet. I did a Spack install of lamps. Now, it didn't have to build it because it was available pre-built in a binary. So that took 75 seconds. So I had a fully functional parallel lamps. Lamps is a molecular dynamics simulation code, popular code in the scientific community, in about 2 minutes. I was able to get this up and available to me And then able, using the E4S Guidebot to help me understand how to run lamps, I was very easily able in a few minutes times to run an example problem of lamps on my laptop with MPI and with threading enabled. And so what we're doing with E4S through the build caches and the containerized instances is to provide easy access to applications that can then be used towards simulation in support of AI. And so reproducible simulation workflows using Spack and E4S, we have access to many libraries and a growing list of applications that allow us to support AI for science where simulation capabilities are needed. All right, I want to move forward now and talk about human agentic or scientific software engineering. So this is very much the forward-looking part. And so I want to look at planning, work management, and testing. So AI, especially as I mentioned, is transforming the software discipline. Software sustainment is also impacted. Code refactoring is easier, we find, as we go forward. I think we could even reach the point where GitHub issues become the source code for PRs. That would be really interesting. I think Agentic is a tremendous productivity boost for greenfield projects. The impact on brownfield is real, but less dramatic, at least so far. I think as a result, more software will need sustainment. And then the question is, how do we support agents as users of libraries, tools, and apps? So I've been involved in a lot of projects over the years. And I've done a lot of work to try to improve software processes among the teams I work with. And so I want to talk about some of the things I've done in the area of planning and try to look forward how those things matter in a human agent world. So one of the things I found really interesting is that human agent collaborative planning seems to be really effective. I'm quite enamored of some of Matt Pocock's work. If you followed him on YouTube, I particularly like Grill Me, and he has variations on that as a way to drill into planning. And I myself have experienced a lot of benefit from conversations with agents on what is it that I want to build and how do I want to build it, and being really thorough with this planning process. In the past, I have to admit that in the scientific computing space, for many teams, the funded research proposal has been the software plan. So in other words, they write a proposal, they get money for that, and then that is the plan. And then they derive requirements, specs, and design by working it out during the code development phase. That was pretty common. But I think we can do better. So I've been involved in scientific software development for a really long time. This code and fix development approach, where people start off, they make visible project, they write codes, they get results, but they don't pay enough attention to the planning. And so as time progresses, they find that they have to spend much more time on planning because the code is brittle. They have to do a lot of recording and spend a lot on reporting to new platforms. And so it becomes very difficult. In fact, projects will die. And so because there's too much time needed to plan and too much time needed for recording and porting. And so the project will die. I have seen this in the agentic world. You see lots of projects, of cautionary AI development. And it's because they use this model of code and fix development. Instead, I think, and this is true before, and I think it continues to be true now, is that if you spend time up front planning, carefully planning what it is you want to create and how you want to create it. It was true back in the past, and it's true now as we go forward as a really good approach to doing scientific software work. And so this is, I think, something that carries forward in time as we go. Okay, that's a little bit about planning, a very tiny amount. But let's talk now about project management. If you're familiar, Kanban is commonly used. It's a very lightweight project management approach. It limits the number of in-progress tasks. Generally, it should be tuned, per the team as you go forward. And the idea of Kanban is to optimize, flexibility versus swapped overhead. No overcommitting. Some looseness and having just the right number of things in progress is very important. I have found it in my career very effective in an R&D setting. We often are discovery-based in our scientific software development. The progress that you made, by integrating one feature can lead to a complete redirection of activity because now you're going to solve a different scientific challenge. And so I've used Kanban on every project I've led and up till today. And I find it a really effective means of managing our activities on our teams. So this is just basic Kanban. If you've had any exposure, you know this. The backlog is any task idea, you trim it. It's a source for other columns. The ready column, it doesn't have to be there, but it's a task plus a description of how to do it. In particular, there are no unresolved dependencies. If you had the resources, you could get started on a task right away. That's in the ready column. And then the in progress column is things that you're working on. Okay, and then the rule of Kanban is you can have only so many in progress tasks. And the limit is based on the experience, and it's a calibration. And also key in this is that you pull work into your in progress column. You are in charge. You can't have someone push work into it that breaks the principles of Kanban. And then the done column, which is useful for just keeping track of your velocity and a record of what's happened. The ready column is sometimes there, and we're going to talk about that. And then the in review column. That is things that have been worked on but need someone to take a look at. And there are all sorts of clever ways that you can add additional columns here. So let's talk a little bit then about agentic engineering so far. So first of all, caution. This is based on only months of experience, right? I personally don't have a lot of experience, but this is what I see as possibilities and trends so far. Humans and agents collaborate on all tasks, but the balance varies. I've seen so far that architecture is mostly a human activity. Planning is balanced. For example, the grill me skill. Development is mostly agents and is highly scalable. And then review is heavily human. So the human roles are domain expert, reviewer, and editor. Human work is more intense now, with high demand. So because we are involved more as domain experts and reviewers, I find this quite cognitively taxing, and others I know also do. And so let's take this then into Kanban, and let's see what Kanban looks like in an agentic world. Okay, so here's a possible agentic Kanban. Okay, backlog, still any task. Ready now was implicit for development, but now let's put that specifically in there. Ready for development. Exposes task parallelism, which is really interesting, right? Because if anything that's in the ready column means it can be worked on right away. Well, we're using agents. We can spin up agents, as many as we want within some economic reality. So that, in a sense, ready for development can be at zero most of the time. In progress, agents are doing it. You have unlimited amount in principle that could be working on. And now I want to introduce a column ready for review. And the reason for that is that we can have a huge in-review backlog because agents can produce candidate features, developed code for you or whatever it is it's working on. And so you, though, as a human, have to review. And so what I'm thinking is the new Kanban rule can have only so many in review tasks. So here what we're doing is protecting the team, so that we can have only so many in review tasks. And to have that, we have to have a ready for review column. And then of course we have the done. And so this is one attempt at how we could do Kanban going forward. So anyway, let's move along a little bit. Then let's talk about testing and agentic scientific software engineering. Agents seem to be quite good at producing unit tests. There is some concern that if you have too many unit tests and focused on APIs, it could actually inhibit refactoring of internal APIs. What kinds of tests can humans provide for scientific codes? We have scientific principles we can leverage. And one example I want to show is something I wrote the HPCG benchmark more than a decade ago, and I put in some what I consider interesting tests that I think are useful as we try to go forward as an example of how we could introduce tests for agentic scientific software engineering. And I call these things meta-computations. They're not needed to produce results, but must always be true and can detect many errors, which is why I wanted them as part of HPCG. HPCG gets rewritten for many platforms for performance reasons. And so I wanted tests that were universally true. And so what are these? Well, what we're trying to do in the HPCG benchmark is exploit two properties: the spectral properties of the conjugate gradient method using eigenvalue clustering. CG will converge in a number of iterations related to the distinct eigenvalues. So independent of the dimension of the system, the number of equations, it's really about the number of distinct eigenvalues. Another property of the HPCG benchmark is the operator is symmetric, and also multigrid is symmetric. So I use these two properties to create tests for HPCG. For symmetry, I used the fact that if I take any linear operator A, then I know the property that X transpose AY is equal to Y transpose A transpose X. If A is symmetric, then A transpose is A. And so I have these two products, X transpose AY should equal Y transpose AX. It's getting a little heavy in the math, but hopefully you're following. And then if I take those differences, they should be zero. And so basically what HPCG does is it computes both of those quantities with two random vectors, and then then scaling for appropriately for the problem size, it should be 0. And so I can compute this, and I do as part of HPCG. Every time you run that benchmark code, this is what happens. Similarly for eigenvalues, I inject large eigenvalues so that there are only 10 distinct eigenvalues in the matrix itself, and then I can use that as a means for testing the convergence of the conjugate gradient solver. And again, these are ways to do testing that are not peculiar to each implementations. So what are some sources for meta-computations? Synthetic operators that I showed, invariant subspaces, conservation principles, and in general, precondition, postconditions, and invariants. And so these are ways as we go forward with agentic computing to put in tests that will be meaningful, independent of the particular details of the implementation. All right. So the last slide in this particular area before I try to sum things up is as part of my efforts, I've been trying to just get a sense of what things were like in the past from all my years of experience in scientific software, and then see how they are different in human agentic scientific software engineering. And so these are books I have on my shelf, and general software. So I think things like the pragmatic program, domain-driven design, the mythical man month, these are all things that are going to be even more important as we go forward than they have been, and they've already been really important. Also, books like numerical computing, Golub and Van Loan, Axelson's book on iterative solution methods. These are all resources for the kinds of tests that I was mentioning that we use like in the HPCG benchmark. And books that I've loved and I've spent many hours with, K&R, Code Complete by McConnell, Effective C++ by Myers. These are books I spent countless hours on. Unfortunately, I don't know that these are so important anymore, as the emitted code is good quality, and I don't know, I feel a bit sad about that, but I like it. overall. All right, so let's talk about discoverability then and usability. So this sums up for agentic scientific software. Discoverability, agents need to discover what's available. And we need to be able to do that through things like model context protocols. We need a registry system for contributing, curating, cataloging these resources. Usability, agents need to know what a product does and how to use it. Seems like skills are a really good approach to this. And there are lots of ways to generate skills files. One is to have an expert sit down and try to use a library or tool or an application, and then ask it to generate the skill file when that person is done. Portability and community. Portability is even more important. We have many specialized devices. We have evolving execution models. Having to be able to separate concerns. Systems like Kokkos and Raja will get us far, but is it far enough? High-level frameworks like PyTorch can be part of the answer. Community becomes critical and should be contain voices that have been largely absent so far. So one opportunity is, as AI does more of the mechanical work, we can focus more on humans. We can focus on software intent. We can focus on societal impact. So what's our first job? If we're going to go in this agentic future, one is, let's take our simulation code and transform it. I think the transformation work that needs to be done in simulation codes is just as disruptive as what we did to go to distributed memory. We have to exploit data parallelism, low and mixed precision arithmetic. We have to redesign algorithms. We have to incorporate AI-based components. We have to prepare for architectural diversity, ensembles, and many other things. And so there's a whole bunch of work left to do. All right. Summary. The value of equation-based simulation software will increase. We'll have more, even though they're cheaper to support. Agentic computing will impact all aspects of scientific software. I hope I alluded to that. There's a lot that we need to do to improve discoverability and usability, and our investment needs to grow. And community is more important than ever. Thank you. Thanks to Google for the chance to speak today. Thank you for contributing to AI for Science, visions, capabilities, and tools. I have a lot of respect and gratitude for what Google is doing in this space. Thanks to the audience. My community are very much newbies in agentic scientific software. We welcome input and collaboration. You can contact me directly at this email address. You can also join our conversations. I put up some pointers to HBSF, to CAS, and then also to a new Scientific Software Horizons podcast that we're sponsoring that you can find on LinkedIn. And I'll stop here. Thank you.
I didn't know about that podcast. Thanks for that, Mike.
Yeah.
All right. So we have a few questions for you that have been submitted, and I think they're all currently from your *1 fan, Uttara Sawant. So we're going to ask Uttara's questions first while other people submit their questions. So Uttara, I'm sorry we can't yet promote you live. We're working on that for the summer, but I'll ask them for you. Your first question was, can you share a few example programming skills required for working in HPC labs? Hopefully GCACC can share pointers into such skill development. I assume she's talking about things like MPI and things like that, but I'm not sure.
Well, I mean, if you want something new, I think actually looking at Julia and Rust are very interesting. You know, we've done much of our work in C++ over the years, certainly Fortran as well. And Fortran is really important, don't get me wrong. Flang is a really important project. But I think one of the really interesting things would be to use some of these more highly structured languages like Rust and Julia as a means to emit new code. So if you're using agentic programming, these languages have stronger error messaging, stronger structure implicit. And I would encourage people to look at that, because we can actually refactor large portions of our software code base using these languages, using agents, and the compiler messages that come back for incorrect code are much more helpful than what is often ambiguous in C++. You can get code that seems to work well in C++. It passes agent tests, it passes things, but it's actually, we're still wrong.
Oh, okay. I'm going to ask you another language-related question since you went down the Julia and Rust route.
Yeah.
What are your thoughts on Python for agentic scientific development? There is a superset of Python that I forget the name of right now.
Mojo.
Mojo, thank you.
Yes.
That is also looks like it might become important. And
Yeah.
my final thought is, why is Fortran not still the most important language in scientific computing since it was the one developed for it? I'm biased. I'm a longtime Fortran programmer and loved how the committee continued to evolve it for scientific computing specifically. So I've hated seeing the migration away from it. I understand it, but I don't like it.
Yeah, JAX is also great, by the way, and Fortran is also good. So I take credit for saying flang the very first time. As it's used.
I want to tell people what that is, by the way.
Flang is the new open source front end for the Fortran compiler. Think of it as like Clang, C-Lang, some people say.
Right.
You know, the front end that everybody contributes to, and then it emits LLVM in the back, and that every vendor compile or optimizes, right, and provides a support for. So I'm very much a believer in Fortran. I think these other languages, in particular things like Julia and JAX, for example, and Rust too, I think, they provide something else really valuable, and that is the support of differentiable programming, meaning that you can compute derivatives through the PDEs, through the physics of it, and you can intermingle AI and simulation in a way that's very intimate and powerful. And so that's one of the reasons why I think these other languages are really attractive. But I'm nothing against Fortran completely.
I'm actually hoping the standards
really
committee.
Compelling. Yeah.
I'm sorry about that. I'm hoping the standards committee decides to adopt that differentials strength into a future version of Fortran, since it does relate so much to scientific computing.
Yes, exactly. Yep.
I'm going to ask one more from Uttara, and then we've got some great announcements coming up. So we will still get you out of here by the top of the hour, audience. But let's see. Can you comment on testing HPC code and simulation versus HPC lab environment? The idea is to manage lab availability versus faster turnaround with simulation.
Boy, I'm not sure how I can unpack that one.
Let me see if I can unpack it for you.
Sure. Thank you.
Actually, I'm not quite sure where Uttara is going with this. I think it might be a simulation versus experiment question. Yes, and she says, yes, it is. So can you comment on testing HPC simulation codes versus lab testing of things? Are we seeing I'm guessing a more rapid prototyping becoming possible, not just with simulation, but now with AI-powered simulation?
Absolutely. In fact, if you look at Genesis Mission and a lot of the expected activities around Genesis Mission, it's spot on. Your question's spot on. And the answer is yes, yes, and yes.